Systems. Yesterday, we had seen that noise right? This was the power spectral density of the noise, and therefore for bandwidth B, I can draw right. Sorry, not this. It should be a parabola. Right. And simultaneously for most practical signals empty SMMF looks somewhat like this. So what we have is this is SMMF and this is the noise power spectral density. Do you see a problem here?
Yeah, it is very much different than the practical ones.
No,
Like,
no,
So
no, no.
it's
like
good, right? I mean, for the frequencies that we are concerned with about in the message signal, they are not present in the noise. So
Or other way, thinking other way around that, see, this is the power spectrum of the noise. This is the power spectrum of the signal. Fine.
okay.
And so you
So if
have
we
a,
add them, then we won't
you
be
don't
able to
add them. You
distinguish.
don't add them. You don't add them. Basically, what happens is that this masks this, or this tries to mask this practically. So think of it as someone speaking and some useless noise. You add the useless noise to something, the noise will mask it. It won't be adding to it. So one thing is that the noise no longer is white. That you can see. Right.
Yes, sir.
So the noise is no longer white. One. Two. This SMMF is this. So so for practical signals, like speech, music. Consider practical signals like speech or music. So have you tried this out? Have you tried to record your voice and take its FFT in MATLAB or Python? Python, I don't know whether you have a direct sound recorder function, but MATLAB has a direct sound recorder function. Has anyone tried that?
Sir, we have done a DFT for a pitch of a ball, like bouncing of a ball, not the human sound. Like along with that, there was noise.
Along with that, yeah, there would be noise. Okay, bouncing of a ball.
Yeah.
But bouncing off a ball is not of much practical use.
Okay.
Okay, because you never transmit or you're never interested in sending the bouncing of a ball to a receiver.
Okay.
Okay, but anyway, the bouncing of a ball is a low frequency signal with some high frequency harmonics, and it will be simple harmonic motion. So you will get more or less a practical periodic signal, right? That's what you might have observed.
Yes, sir.
Yeah. So now instead we have for practical signals like speech, music, if you try the recorder and take its FFT, you will see a signal like you will see a frequency spectrum like this if you try to plot it. And even now here, once we are talking about music, so the voice, so we can hear in the range 0 to or 20 hertz to 20 kilohertz, right?
Yeah. Yeah.
And the speech signal is limited to 4 kilohertz or 3.8, 3.6 kilohertz to be precise. So uh, apart from that, everything else is higher frequency. So consider a music, consider a song where the vocals and the drum beats, they're all confined. So vocals are loud, drum beats are loud. The music is relatively softer.
Yes, sir.
All the string instruments are relatively in the background as compared to this, as compared to the vocals and the drum beats. The drum beats are actually the loudest.
Yes.
So those are at the lowest frequency because you beat at the base frequency of a drum. If you beat it, say, once every second or twice every second, the base frequency is 1 hertz or 2 hertz, which go and the significant harmonics of that. Say even if you beat a drum 10 times a second, which is ridiculously fast, that frequency would be 10 hertz and the significant harmonics would go up to 100 hertz or 200 hertz at most. Right? Because we know that all the practical Fourier transforms that you have considered till now, the effect of the signal decays or the contribution of the frequency decays as you go into the or as the harmonic index increases. We have observed that.
Yes, sir.
Yeah. So the contribution of the smaller frequencies is large, and the contribution of the larger frequencies, the violins, all the string instruments that play at higher frequencies, their contribution is relatively smaller,
Yes, sir.
but it's nonetheless important. You cannot, and so the purpose of music is enjoyment, not mathematical analysis. Yet you cannot enjoy music, or you cannot enjoy piece of music unless all the instruments are present and all the instruments are present in their appropriate proportion.
Sir, just one
Yeah,
doubt.
Rahul.
Like in terms of contribution, are you talking about the amplitude of that particular
The
thing, or
amplitude of
like
that particular frequency, yes.
okay? So in general, drums are of higher amplitude. Even like we can even make this like the violin part or something of higher amplitude, right?
But that will become unpleasant.
Okay. Okay. This is the general structure of any music. Okay.
Yes, the general structure of any music. We'll discuss this in greater detail, possibly once we discuss source coding in your digital communication, or if you ever do a course on multimedia communications.
Okay.
So this is related more to perception, less to actual math. But
Okay.
what happens is that for most signals of practical use, the spectrum looks like this.
Okay.
Okay. Now the problem is that in a practical signal or for practical signals, the amplitude reduces as frequency increases, and in case of noise, it is the other way around. Right. So noise, the noise amplitude or the contribution of the noise for FM increases as the frequency increases. Right. So we have a problem that stronger signal components have weaker noise and weaker signal components have stronger noise. Now again, we'll come back to music. If you imagine a symphony or some music where the high frequency instruments are noisy. So whenever there's a violin, you simply hear garbled noise. Would you like that?
No.
So the key here is to preserve all the frequencies, or the key here is to have equal effects of noise on all frequencies, so that even if there is even if the noise is white, then you say that okay, the noise affects those frequencies proportionately, and I have an equal distribution of noise, and there's the signal to noise ratio is a valid measure. But now, if the noise affects different frequencies differently, the signal to noise ratio is not an efficient measure, and you actually, the higher frequencies, because of the lower their natural lower amplitudes and higher noise, get hit much worse, right?
Yes, sir.
So therefore, in this case, the fidelity of reproduction of an FM system becomes questionable. Fine. And now the simplest thing that we can do to counter this order to counter this Just a second. Yeah. In order to counter this, we can artificially enhance the, we cannot do anything about the noise, but we can artificially enhance the weaker or the, actually not the weaker, but the high frequency hence the, we can artificially enhance the high frequency components, the signal, this before transmission. This is called pre-emphasis. So we emphasize the frequencies of interest before we transmit them, and this thing is, or this idea is called preemphasis. And since this is a, since preemphasis is a deterministic process, we can, sorry, reverse this at the receiver. That process called de-emphasis. Fine. So, and therefore, if we use a filter HP for HPF with a frequency response HPF for pre-emphasis, we use HDF for the simplest example is HPF equals 1 plus JF over F naught, and 1 over F naught is some constant cutoff. Fine. Any problems with this?
No, sir. No problem.
No problem. Great. So Now we come to the last topic for this noise in analog modulation systems, and that is so there is one topic that I want you to read yourself. That's just that's just some storytelling. So ProKIS 5.4 comparison of analog modulation systems. So basically they compare AM, different varieties of AM and FM in terms of their spectral and power sees terms of noise performance. So it's just it's one page and it's just some storytelling. So I'm skipping this here. So now the last topic that we'll cover in this chapter is characterizing noise in communications, or link budgeting. Let's call this, let's use the proper word, and link budgeting. So in order for link budgeting, we know that whenever a signal propagates through a communication channel, it gets fine. So you have electromagnetics you are doing this semester, right?
Yes,
Yes,
sir.
sir.
So have you covered transmission lines?
No, sir, not yet.
Okay. Waveguides?
No, sir. We are. I think that is our last topic: waveguides and antennas and transmission
Transmission
lines.
line. Okay. So that's a problem because so basically you can see that any transmission line is basically a network of resistors. And what happens is that basically you can in transmission lines, what you will see that transmission lines, the way the lines through which these electromagnetic signals transmit are can basically be modeled as a network of resistors, capacitors, and inductors, and with some parameters and say microfarads per meter and ohms per meter, etc. Resistance, capacitance, and because of that, the signal gets attenuated. So if I send signal ST, the received signal RT is RT equals alpha ST plus WT, where this is the rectified Gaussian noise and attenuation. So all of us know that signals become weaker as they propagate. Fine. Have you heard of the Friis equation?
No, sir.
No, sir.
Okay. Okay. Consider a wireless medium. Wireless medium with, so an example. So consider a wireless medium with an LOS link, sorry. So this is the transmitter, this is the receiver. You are transmitting the signal ST from here. Fine. Now, when you are transmitting ST, basically this ST is in the form of an electromagnetic wave. But the problem is you don't know what is antenna gain. Do you know what is antenna gain?
No, sir.
Okay. Okay. We have some problem. So because the first thing that you might notice is that antennas are passive elements that you might know. So how do I
Yes, sir.
define the antenna gain? So that actually I leave up to your electromagnetics or your electromagnetics course. I cannot discuss that here. But at the same time, because there is something called the antenna aperture, there is the antenna gain. So basically, what you can say is that uh, the strength of the electric field. So this you know that if this behaves like a point charge, like say this is the distance, this is distance x. So if you basically transmit these signals as electromagnetic waves, and electromagnetic waves you know that are nothing but changing electric and magnetic fields, right?
Sir.
Yes, sir.
So you say that for starters purposes, let's say that in order to transmit the signal, I'm generating a charge over here, this ST, and so I'm generating a charge QT, or I'm generating a charge which is proportional to ST. Fine. And so this charge is proportional to ST, or uh, this ST is the charge at this transmitter. There's a point source at the transmitter, and that has a charge ST coulombs. So this ST is the point charge, and because of that, the field at a distance are x. Therefore, the electric field at a distance x is ST by 4 pi epsilon naught x square. Right? This will be the electric field.
Yes, sir.
Or this you can say that this has the units of watts per meter square. Okay, so yeah, let's not go into that. So anyway, I'm just giving a rough sketch of the things. And now this will, the electric field that is absorbed by an antenna at this point will be the proportional to the antenna, proportional to the area of that antenna.
Yes, sir.
So so basically what you say, the basic idea is that the signal attenuation increases with the distance between the transmitter and the receiver, and this alpha is actually proportional to 1 over r square. Fine. So this much you understand that this alpha will be proportional to 1 over r square.
Yes, sir.
Yes, sir.
Or 1 over x square. So this is the key idea, that the attenuation increases as the distance increases. And now you are familiar with the notion of decibels.
Yes, sir.
Yes, sir.
Where did you do this?
Decibels, sir.
Huh?
School.
Decibels.
Decibels.
School and even in college, sir.
Ah,
School.
Last
Where?
year also,
Which,
control systems also we use decibels for plotting the magnitude
okay,
spectrums.
so in control systems you would have used this right?
yes.
Yeah.
Yes,
So
sir.
there's a slight difference for communication systems, or actually, so this is in terms of amplitude. This is gain dB when you are talking about amplitudes. When you are talking about powers, so say you have the signal to noise ratio. You want to define the signal to noise ratio in dB, then SNR is, or SNR dB equals 10 log to the base 10 this. Fine. So this is how it is defined in terms of power, which makes some sense because power is generally considered to be the square of amplitude. So this moves out.
Yeah.
Fine. So now based on this, so we can say that given that, and I also define dBm. So first I define dBW, decibel watts. So this is power in dBm. dBW is 10 log 10 power in watts. Decibel in watts. Fine. This is just an expression that you may have to remember.
Yes, sir.
And then there is dBm, d small d, lowercase d, capital B, and lowercase m. Decibel, actually decibel milliwatts. This is 30 plus. Yeah. Can you tell me how does this come?
So 10 to the power 3
Yes,
wala
sir.
factor.
Yes, simply that. So this. So we generally in the communication systems we generally talk about SNRs in terms of decibels. Fine. We generally talk about the SNRs in terms of decibels. And so with this out of the way, I can say that if have an amplifier, then P out dB equals P in dB plus P out in dBW. P out in dBm equals P in dBm plus gain in dB. Fine. I can write the input and output powers in terms of gains.
Yes, sir.
Makes life simple. So if I say that I have a signal xt with a power 20 dBm and the received the receiver noise is at 5 dBm, then the received SNR is how much?
Sir, 15.
15 dBm or 15 dB. This is dBm, this is dB. So signal to noise ratio. So the signal to noise ratio will be in decibels because the watt cancels out. Fine. Now, if xt is 20 dBm and is amplified using an amplifier gain 3 dB and then transmitted, then the presence of noise at 5 dBm, the SNR is 20 plus 3 gain minus 5 dBm equals 18. Fine.
Yes, sir.
Basic arithmetic, but there's a catch. Now, if xt is 20 dBm and the noise is 5 dBm and I amplify the received signal yt equals xt plus wt by 3 dB, then the received SNR is 15 dB. Why? So what happens? What's the difference between transmitting before, amplifying before transmission and amplifying after reception? What changes?
Sir, here we can't add the 2 dBms.
In the second case,
Yes, sir, because
so there is go a level lower actually. There is something more fundamental amiss. See, in the first case, what is happening is have a signal boost by 3 dB, transmit, noise added, received with a higher SNR. Fine. This was the first case.
yes, sir.
In the second case, have a signal, transmit, noise added, received, boost by 3 dB. Fine. So in this case, you are first boosting the signal and then adding the noise. Here you are receiving signal plus noise and then boosting that by 3 dB. So the signal as well as the noise gets the boost. So you don't gain anything.
Okay, sir. Okay.
Okay. So see, in this case, you will be just boosting xt. Here you are simply boosting xt. Here you are boosting this yt, which is xt plus wt. So the signal will be boosted because you cannot, once you add the noise to the signal, there is no way you can remove that noise from the signal.
Yes, sir.
So since you can no longer remove the noise from the signal, you have this problem. So you always have to pre-boost or post-processing at the receiver is not a good idea. So on a related note, also all the amplifiers are themselves made of active and passive components and are themselves sources of noise. So in addition to amplifying the noise supplied to them. All such components add their own noise to the system. Fine. Makes logical sense?
Yes, sir.
Good. So now consider an amplifier with a gain G, bandwidth B. So if we consider the equivalent bandwidth, we assume that the amplifier is flat, being fed with wide Gaussian noise having a PSD KT. Fine. Where T is the ambient temperature. This is fine. The output noise in this case, so output noise. So input noise eta input, or rather P input, the noise power at the input is KTB. P output will be G times KTB plus internal plus internal noise power. Fine. Any doubts with this?
No, sir.
Okay, this makes sense, right? Because so yeah, this makes sense, right?
Yes, sir.
Yeah, this, and now this equals GK B T plus P internal by. Fine.
P and internal is the internal noise that is
Yeah,
present.
so I'll not present the internal noise added due to the, or by the amplifier, not due to the amplifier, by the. Fine. This, and this I call as TEQ and write down as equivalent noise temperature. Equivalent noise temperature of the amplifier, and the output power is GKB T plus T. And SNR input, if it was PS by PN, SNR output for this amplifier will be GPS by Pout or Pin. Right? Equals GG cancels out, PS divided by KB, actually KBT, 1 plus T equivalent by T equals PS by, or yeah, PS by Pin times 1 plus T equivalent by T, and this equals SNR in divided by 1 plus T equivalent by T. Okay, this thing is denoted by a capital F, and is called the noise figure of the amplifier. So an amplifier with a low noise figure reproduces the input signal with a high fidelity, and is therefore called a high fidelity receiver or a hi-fi receiver. So this term hi-fi actually came from hi-fi audio systems that became popular after the Second World War, and they were so expensive that only uh, hi-fi people could afford them, and therefore this hi-fi stereo system actually became synonymous with rich or snobbish people, or people who like to show off. Fine. So this is called the noise figure of the amplifier, and in general, SNR out equals minus 10 log F, or SNR out dB. I should write this in dB. SNR out dB is minus 10 log F plus 10 log, sorry, yeah, plus SNR in dB. Fine. And this represents the loss in the SNR performance due to the internal noise of that amplifier. Fine. And finally, it is, because we are running out of time, easy to show that for a cascade of n amplifiers with gains G1, G2, Gn, and respective noise figures F1 to Fn, the overall noise figure can be given as F equals F1 plus F2 minus 1 by G1 plus F3 minus 1 by G1 G2 plus Fn minus 1 by G1 to Gn minus 1. This beast. Sorry, Fn. So this is F subscript n minus 1 and this is G subscript n minus 1. Fine. So this, and we'll stop here. I hope to finish this discussion today, but it seems that it will spill over into another 15 to 20 minutes. So we'll stop here and continue tomorrow. Any problems or any doubts?
No, sir.
Okay, excellent. So we'll continue tomorrow from the same point.
Sir,
Yes,
sir, can I ask it out regarding restless quiz?
absolutely not.
Okay, fine.